So I'm going to give you a quick rundown of the subjects in Classical Mechanics PHY 221. This will mostly be used by students preparing for exams. So just a quick bit of advice before you start. The first thing you do when you open the exam paper should be to read the whole paper. Bear in mind that PHY 221 has a compulsory question, which is question 1. And so do be aware of that and make sure you do question 1. But it is not always true that questions 2 and 3 are the questions on which you're going to get the most marks. So have a look at all the questions and form a strategy before you start writing on the exam as to which questions you're going to do. The other thing is, do bear in mind that some marks are easier to get than others. So try, if you get stuck, not to get too bogged down in doing any particular piece of a problem which you're finding hard. Give up quickly, move on to the next marks you can get more easily, and then come back to the sections which you had most trouble with if you have time at the end. I should wish you all the very best of luck. So we're going to go through the exam from 2015. I'm hoping that that will be the best form of preparation that I can supply you with. If you have questions about the course, then you can send me email in the time period up towards the exam, and I shall try and answer your questions. So the first part of the 2015 question in this time contains sort of a smorgasbord of different topics. That isn't always true. It wasn't true of the last exam, but it is true of this exam. So the first thing that it asks about is a Lagrangian. So you have a system that has a Lagrangian, which is given by 1/2 mz dot squared minus mgz. So this is a function of only one coordinate. So you have a generalized coordinate z, and z dot is the velocity associated with the generalized coordinate z. Okay? And it says attain the equations of motion for this object from the Lagrangian given above. So you're going to get the equations of motion by writing down the general form of the equations of motion in the Lagrangian formalism, and that's this. So you've got d by dt of the partial derivative of L with respect to z dot in this case, because z's your coordinate, minus partial L with respect to z equals 0. So those are your Euler-Lagrange equations of motion, and you should remember the form of that equation. If you have a problem which has more than one coordinate, so say you have a particle moving in 2 dimensions or 2 particles connected by a spring or whatever it is, then for each coordinate, so say the 2 particles are free to move on the x-axis, the displacement of each particle would be a separate coordinate, and you'd end up with 2 Euler-Lagrange equations of motion, one corresponding to the motion of the first coordinate and the other corresponding to the motion of the second. Okay, so in this case we've got to calculate these partial and ordinary derivatives. So the first one we're going to do is the easiest one, which is the partial derivative of L with respect to z. So that equals d partial with respect to z of 1/2 mz dot squared minus mgz. Now, important point here, the partial derivative of z dot with respect to z is 0, because z and z dot, for the purposes of figuring out the equations of motion, are considered independent of each other. And similarly, the partial derivative of z with respect to z dot, well, that's 0 as well. So the fact that those 2 partial derivatives are 0 is itself a very useful thing, because it means you can simplify all of these kinds of partial derivatives. So if I do the partial derivative with respect to z of this whole expression, the only z that's in here on its own that isn't a z dot is the one at the end. It's the one in the minus mgz. So that partial derivative completely ignores the 1/2 mz dot squared term and just goes straight on to the minus mgz, and so you get partial with respect to z of minus mgz, but partial with respect to z of z is just 1, so that's just minus mg. So the partial of L with respect to z term is just minus mg. So let's erase partial L with respect to z and write minus mg. And of course, don't forget the minus sign, that's important. So that's the first partial derivative we've got to do. The second one is the partial derivative with respect to z dot of 1/2 mz dot squared minus mgz. Now this partial derivative ignores the z term because there's no z dots in this term. The only z dots in the equation are in the first term, that's the only term the partial derivative acts on. So you have partial with respect to z dot of 1/2 mz dot squared, which is 1/2 m times 2z dot, because d by dz partial with respect to z dot of z dot squared is 2 times z dot to the first power. It's the ordinary way of differentiating polynomials that we're doing. And then the half and the 2 cancel, so you get m times z dot. So that's the partial derivative of L with respect to z dot. But notice we need the time derivative of that. So we need the time derivative of the partial derivative of L with respect to z dot, which is just the ordinary time derivative of mz dot. Now m isn't a function of time, but z dot is. Z dot is just dz by dt. So that's m times d by dt of dz by dt, which is m d2z by dt squared. So we can replace the first Euler-Lagrange equation with the first term in the Euler-Lagrange equation with just m d2z by dt squared. Right? And so now we've actually figured out the Euler-Lagrange equations of motion. Everything we need is in the box. So we have m d2z by dt squared minus mg equals 0, or m's cancel here, and the 2 minuses give you a plus. So d2z by dt squared plus g equals 0, or moving the g to the other side of the equality sign, d2z by dt squared equals minus g. So this corresponds to an object accelerating downwards with acceleration g, magnitude g, I guess. Now, that will get you a lot of marks if you did all of that. The one thing I would say to watch out for is when you're doing these questions, do be careful to make it very obvious which of the derivatives you are doing. So if you have a partial derivative, write it with a very curly d sign. So d by dz partial should be written with a very curly d. If you have a total derivative, an ordinary derivative, write it with a straight up d. And make it very obvious which you're doing, because if you make any mistakes, the person marking your exam has to figure out whether you knew which of these derivatives you were doing. If you make it ambiguous, if you write something which is sort of halfway between a partial derivative and an ordinary derivative, say you do this kind of thing, it's not at all obvious to me what that means, or to whoever's marking the exam. Of course it will be me. And so it will be more difficult for me to give you partial credit if it's ambiguous like that. So do try and make it clear from your writing whether you're doing a partial derivative or an ordinary derivative.